Hi, yeah, my name's Ryan. First, I'm going to try and convince you guys that, the human forelimb can be equated to the avian neck. Now, it might seem a really weird comparison to make, but actually, what do we use our hands for? Well, later on, we'll probably all be picking up pints with them, but that's completely fine. We use it to interact with our environment. But when we think about birds, yes, their wings are fantastic and well adapted, perfect almost in terms of flight. But when they want to manipulate their environment, they can't really use their forelimbs. They're kind of, in one of a better word, they're a bit useless for it. So they have to use their hands as essentially, their beaks as a surrogate hand. So if we extend that analogy, it's more of the neck is more of a surrogate arm. It gets the surrogate hand where it needs to go. So there's a lot of extra evolutionary pressure on the neck, which, as a general blanket statement, biomechanists for the last 100 years have said, well, this is why we get such vast, diverse neck morphologies in birds. And that's really the crux of my PhD. It's such a broad blanket statement that we don't understand any of the forces behind this. We don't understand the drivers behind this evolution of huge neck morphology and disparity. So the way I'm trying to understand these drivers is through regionalisation. Now, the spine is regionalised as a whole into distinct regions of vertebrae, and these vertebrae form distinct functions. Now, very briefly, I'm not going to go into too much genetics, but this is controlled by Hox genes. And more recently, we found out that within larger regions, so for example, the cervical region up here is actually regionalised further into subregions. And it's these subregions is what I'm going to be studying to try and figure out how this sub-regionalisation varies throughout aves. Now, I'm going to very quickly take you through the methodology. I've got 52 birds in my data set, which each have around, on average, 15 cervical vertebrae. So I've had to segment, digitize, and landmark around 600 cervical vertebrae. So that's been a fun 18 months in my life. We've then taken that and landmarked them, performed PCA on them, and then from that we get principal coordinates analysis, which is over here, and we get cluster analysis over here. And this is essentially where we get our regions from. So if I colour them in to give you a bit more of a hand there, that's how we get our regions. Very quickly, I know there's a lot of fresh-faced undergrads here. If you are at all interested in geometric morphometrics or shape analysis, come grab me after. I'm more than happy to talk about it. But really the main outputs that we get from this is three. We get the number of regions within the cervical column, we get the size of each region, so we get the variation in the amount of cervical vertebrae associated per region, and obviously because it's a geometric morphometric analysis, we get the actual physical shape change of these cervical vertebrae. Now there's a reason why number is so small compared to the rest of the other two, because I'm only going to be talking about these two, size and shape. And that's quite obvious, because when we look at the number of regions within the cervical column, there's always 5. That's a really strong result we've got, and that's for all 52 taxa that we've found. Well, the first thing I want to talk about is the size, so the number of cervical vertebrae associated with each region. Now, as you can see here, it changes drastically. Now, I want to see whether it's ecological forces which drive this, or if it's more biomechanical forces, ecological like diet and flight style, or is it more to do with neck length, since that changes a lot throughout modern birds. Now, if we look at ecological drivers behind region size, we actually see such a jumbled mess of a pattern. There's no significance here, no matter what stats test I throw at it. I can't find anything meaningful in the ecological results when we plot the subregion number versus the total number of cervical vertebrae for each species. So, but when we look to more biomechanical factors, such as neck length, we see quite a nice pattern. So in these regions here, the ones that support the head, region 1, and then region 5, which is the one that supports the neck as a whole, these very biomechanically important regions, which provide strong stabilisation within the neck as a whole, they don't really respond to neck length. But where it gets really interesting is regions 2, 3, and 4. Now we compare regions 2, 3, and 4 in like small neck birds, such as these two, compared to longer neck birds. We see a big increase in the sizes of regions 2 and 4. This is where neck elongation is happening at these specific sites, whilst region 3 gets a lot smaller. So from this, I really want to say that it's more biomechanical factors that seem to be influencing region size. Now, I'll come back to the reason why I think this, but before that, I want to go on to shape. Now, I think the main factor that affects the way our vertebrae is split into different regions is this feature of anatomy up here, which is the neural spine. Now, as we progress through each different region, these are just examples of different regions in a penguin, which kind of show the anatomy of a neural spine in a much simplified way from the geometric output. We get really large neural spines in regions 1 and 2. We get a flattening off in region 3, then an increase in size in region 4 and 5. Now, just to prove a point that this actually does happen in real life, not just on my computer screen, here's kind of the outlines of the neural spines in an actual specimen. So, to me, this is, well, about 12 months ago, this was the inkling that there was some kind of general pattern within birds in terms of how neck morphology changes throughout the cervical column. Obviously, so far, this is entirely qualitative. To get anywhere, I thought, oh, well, I've got to put a statistical value onto it. Now, it took me a while to try to find out what test was most suitable for this. But what I came up with was, well, what I found in the literature was phenotypic trajectory analysis. When you compute it and put it through R, it gets a really horrific looking graph like this. I'm going to try and walk you through it because it is quite an important and new results. Some of you who've seen this talk before might not have seen this, so it's brand new. So what this is essentially a morphospace with the mean shape of each region for all my birds plotted onto one plot. And in this case, we take a certain factor. So the factor in this case is flight style. And we take, within that factor, an individual group. So here we've got terrestrial birds. Now for this group, we plot the mean shape of region 1. We connect this to region 2, connect this to region 3, and so on and so forth, until we can essentially quantify on this PCA space the entire shape change throughout the entire cervical column. Now, we take this for terrestrial birds and then compare them to other groups within our factor. So soaring birds, intermittent bounders, flap gliders, and when we compare this not only for different groups within the same factor like flight style, but also to diet and also to phylogenetic groups, lo and behold, it's not statistically significant at all. But this is totally fine. Now, for a long time, I was kind of low and like down, like, oh, I've not got any statistically significant results, you know, I'm never going to publish anywhere. But actually, it's not the case, because I went back to my original qualitative hypothesis and saw that the inkling that I had about this general patterning of shape change throughout the avian neck might well be true, because as we saw previously, the avian neck shape change isn't significantly different amongst different groups. So if it's not statistically significantly different between these different groups of birds and between these different factors, then all birds seem to follow this general shape change pattern. So why is it that we see this pattern if it's so prevalent and important throughout all birds? Well, I've talked a lot about neural spines, but not really explained what they do in terms of morphology and function. Well, neural spines are still circled in red. They're associated with dorsal musculature and dorsal ligaments, which support the neck as a whole. They stabilize the entire neck and are crucial for basically everyday use of the avian cervical column. Now, if we bring this all together, and when I was talking about region size, we saw that regions 2 and regions 4 are associated with neck elongation. So as the neck's getting bigger, these two regions, which are also associated with larger neural spines, so you're getting more neural spines, which is more surface area for muscle attachment sites. So you're getting more of these support muscles to support along the neck. So it kind of biomechanically makes sense that why you see this general pattern and why you're not really adapting to different flight styles or diets, because it's more about adapting to a longer neck. So I think that general biomechanical factors are really controlling region size in modern birds. And combine this with the fact that I think region shape is governed by a more general pattern of neck morphology, which I think is more of a response to a longer neck, which I think there's no one specific function, or this may be diet or flight style, which is controlling neck morphology. I think it's more adapted, the avian neck is more adapted to like everyday use, which is it's a term that's been around for quite a while, that it's not really adapting, apart from in very specific cases, like for example woodpeckers, they do a very strange thing that not a lot of other birds do. But the avian neck is essentially a jack of all trades. It can do anything that a bird needs to do, just like our arms essentially do. I'm just going to skip over that, and thank you very much for listening.